Gain is a term that gets thrown around a lot when talking about audio, and it's not always used correctly. You've probably heard people say, turn up the gain, or it sounds gainy, or even the terms gain structure or gain staging at some point, and probably assumed it meant volume or loudness or even distortion. But to put it simply, gain just means to increase. In a piece of audio gear, the gain control will simply turn up whatever circuit it's connected to. You use the gain to increase the level of the electronic signal in that circuit. This process of increasing the gain to create more loudness is called amplification. Gain structure or gain staging is the concept of how an electronic signal is increased over a longer chain of electronic circuits and what order they're arranged in. Our gain structure tells us at what point in our signal path there is a stage of gain and how that will affect the sound in the rest of the circuit. Understanding the gain structure of our system allows us to make the very best choices to achieve the cleanest sound. But what does that even mean? The cleanest sound. Well, we've all heard bad sound, right? When something sounds bad, it's usually because the parts of the sound that we want to hear are clouded over by unwanted sounds like hum, hiss, or buzz, or sound distorted or fuzzy or crackly. It turns out that most of these problems are caused by poorly used gain structure. The best way to understand where the bad sounds come from is to learn the concept of the signal-to-noise ratio. The signal-to-noise ratio in a piece of equipment or sound system is, in simple terms, how many decibels fit into the system between the point of the sound being audible and the point of it being so loud that the system is overloaded. Decibels, of course, are the unit of loudness. More decibels means a louder sound. Fewer decibels is a quieter sound. When we're talking about decibels and loudness in a piece of electronic gear, the decibels are a measurement of electronic energy rather than acoustic pressure. In this case, more voltage means a louder sound. And so we use a unit of measurement called dBV, decibel voltage, which is the intensity of the electricity that is our sound inside the system. So in any electronic system, there exists some naturally occurring inherent electronic noise. Every electrical device that exists creates some of its own noises, simply by the nature of how electricity works. Electricity is the flow of electrons from one atom to another through the wires. And this process gives off heat and often vibrations. And that heat and vibration makes a sound. It's usually very quiet and can't really be heard. But in an audio system with lots of gain stages, where we are constantly amplifying the electronic signal, this naturally occurring noise can become louder and louder. This naturally occurring inherent noise inside of an electronic audio device is called its noise floor. When a device is made, it's tested to see what the dBV level of its noise floor is. And that value is included in the technical specifications. Higher quality devices will have a lower noise floor, which means that they make less of their inherent noise. So why do we care? Well, if the equipment is making its own electronic noise, and we want to send an audio signal through it, that means we need to make sure we can hear our audio signal over top of the noise floor. Our signal needs to be louder than the noise floor. And then if our signal is only slightly louder than the noise floor, and we use the gain control on the device to turn it up louder, we will also be amplifying the noise floor along with it. So this is where sounds like hiss and hum come from. These are the inherent noise floor electrical sounds of the device being amplified along with our signal. So we need to be sure we're using a loud enough signal with a strong enough voltage to overcome the noise floor. But then why not just make the signal super mega extremely loud all the time? Doesn't this just mean louder is better? No, because every device has a limit to how much voltage can safely pass through it. Our signal is voltage traveling through the device, and the components that it's built out of can only handle so much voltage for a lot of different reasons. Again, we are talking about signal, which is electrons flowing from atom to atom within the wires of our devices. There are only so many electrons in so many atoms to carry this signal through the circuit. There's a limit to the level of the flow of electrons through wires and components. Every device will have its own specified number of dBVs that it can carry before it hits that limit. If you try to push more through that circuit, it will cause the sound to lose clarity. The electricity will still pass, but it won't have the same accuracy. It will gradually just become a mush of electricity that will sound worse and worse the louder it goes as it gets forced through a circuit that can't carry it. And eventually, enough voltage will even cause the components to break and burn, causing real damage. But long before it causes real physical damage to the equipment, it will cause audible damage to the sound. And you'll hear distortion when you exceed the capacity of a device. Let's look at what's happening to our electronic signal waves in between the noise floor and the limit of our circuit. We can draw an electronic signal wave exactly the same way we drew our waves that represented acoustic air pressure. There's a wave of positive electron flow followed by a wave of negative electron flow as it travels through the circuit. It's literally an electronic representation of the pressure wave in the air that has been converted to electricity by our microphone. It's the same diagram of a sound wave that we saw before, but now it represents voltage instead of acoustic pressure. So now let's look at a graph that shows no signal. The noise floor or inherent sound of the device will be really low, but it will be there. There might be a few different kinds of sounds, like hum and hiss and buzz, so we can draw a few different waves. Now, if we send our sound into this circuit, we need to make sure it's louder than these noises. If it's not louder, it could end up getting mixed up with the noise floor, and then when we try to turn it up using the gain, we would just turn everything in the circuit up and end up hearing the sounds we don't want. And then here's the other side of the scale, the maximum level that the circuit can handle. Here's our audio wave traveling through the device. So what happens when it's too much for the circuit? Well, it actually gets held down or clipped off. It changes the actual shape of the waveform. The wave gets held down as the electrons get smushed through, and the smooth curves of our wave get cut off. So what do you think this waveform would sound like if it were played back through a speaker? It would be a buzz or a crackle, the sounds we call distortion. We use the term distortion because that's exactly what's happening to the waveform. The circuit is distorting it. Sometimes we also say clipping because of the way the crest of the wave gets clipped off. Sometimes we'll even say square wave because it's been essentially turned into a square. Now, there are a lot of devices that use distortion purposefully, especially electric guitar-related devices. At some point in the mid-20th century, people realized the sound of an overloaded guitar amp made the tone extra interesting. And ever since then, distortion has been used creatively to shape sounds and create unique tones and textures. When you see a gain knob on a guitar amp or pedal, this is the dedicated amplification stage for driving the signal extra hard into the circuit to purposefully overload it. In this case, the gain knob is intended to add distortion. But that doesn't mean gain always adds distortion. It just means in this case, the amplification is being done intentionally to create a harsher sound by exceeding the capacity of the circuit. So now we know the risks of having too much or too little signal. And maybe now you can also understand how we would need to be selective when we choose to amplify or increase the gain. In order to have the cleanest and clearest signal for the sound that we desire in our mix, we need to always be aware of the different stages in our circuit that it is being amplified, or its gain stages. Keeping in mind that we want to have enough signal to get over the noise floor without overloading the circuit, we can now choose when in the process to amplify or adjust. to keep it loud enough without causing distortion. If you're hearing noise floor or distortion, you can always have a look at the flow chart for your device or sound system, and then check what you've done at the various gain stages to see if maybe you've turned up the noise floor or clipped the signal. The goal is to understand the flow of your system enough so that you won't have to always look at your diagram whenever you hear a problem. With time and practice, you'll hopefully be able to hear a sound and know which stage of the system you need to address to make it sound the way you want it to.